All right, so just very quickly to wrap up that because we are reaching to the end of the lecture. So today this week, past week perhaps, we finished the sensory portion. Um, Sensory portion include the sensory one, somatic, sensory two, the eye, sensory three, the visual, and then we will maybe later this week I will post the lecture for the next week, and basically that will end it, right? I think that's a plan. So I already finished the motor, so the next portion will be the motor. I finished the motor, the lower motor system, the cerebellum and the vestibular. I already finished the lecture. I'm still working on the very final piece, which is the basal ganglia and the cortical portion, cortical integration. So I will finish that, and then that's it. As for this week, so if you assume that everybody did the quiz 6, so quiz 6 is about the the beginning of the neuron, so it's a foundation of the nervous system, and also the sensory one. So that's the and by this Friday we will have another quiz that is the sensory 2 and 3. Sensory 2 and 3 are the cranial sensory nervous system. So let's look into that. Basically, I think this portion is getting, gradually we are beginning from the more fundamental and getting more and more complicated. So that makes sense. And the so in the beginning, in this portion, we are talking about the eye. So what do you need to know about the eye? Basically, eye is, as you everybody know, is quite complicated. There are different components to it. So I try to point these essential components and explain using one or two slides to explain what you need to know about that. So, for example, in the beginning is the cornea. What do you need to know about the cornea? Transparent. Well, we don't need to learn that. We know that, right? And but one thing you need to know is that it's transparent, but it's not dead. It has cells. It has actually layer of cells. So it feel, it feel pain. Sorry, there are no receptor with it. So that's what you need to know. And another thing you need to know is that it's a biophysical feature, biophysical characteristics. That is this refractory. And this go back to the time that we learned about the physics, right? The lens, the refractory, ref, refract. I've spelled it wrong. Refractory, refractory, man. It should be refractory. Refract. Refract. Yeah. Refract. Refract. That makes more sense. Yeah. Refractory. So it means that the light will be bended. And then, so the way that we bend light goes through two parts. One is in the cornea, the other one is the lens. The major refractory is in the cornea, even though the lens only do a little portion, but the lens is one that we can control. Control the lens refractor is called the accommodation. So that's right here, lens and accommodation reflex. Okay, so let's go just one. And a vesicularity means that there is no blood vessel to it. So that's very important, but that's kind of, we know it. But here, just showing you that why is that important. We know it's live. We know it's transparent. So apparently there's no red blood cells underneath that. So it's transparent. There's no color. And but the clinical relevance about this one, no blood vessel goes through it, is that this is a good organ to conduct the organ transplant because there is no blood vessel, there is no immune cells, there is no rejection. Well, our body won't know that is transplanted. So that's that, and then because well, here we have live cells in the cornea, and we don't provide it blood, and then how will we provide the nutrients, oxygen? We use this flow. This is called aqueous humor. So that flow, continuous flow, that basically is very similar like the lymph, the lymph vessel. So it basically go from the capillary and filter through it. So it's like pure fluid, but contains the oxygen and the glucose, and that can be used to neutralize the cells. And this flow is a living flow. It's not like dead water, living flow. So keeping it flow is very essential, and that leads to an important concept about intraocular pressure. Because if that flow is blocked, then there will be accumulation of the fluid that increase the intraocular pressure. So that is very important because if we don't know, we may think that intraocular pressure is in the eyeball. So it's like entire eyeball. It's actually the very early, very anterior portion, this anterior chamber, posterior chamber, that's the region to impulse to provide this pressure. So that's also very important because that has clinical relevance to the glaucoma. So that's the if the intraocular pressure can be easily detected. It's non-invasive, just right here. We can use very simple device to detect the intraocular pressure. And if it's too high, then it's an indication of the glaucoma. So if you have regular like visual exam, doctor should be able should quickly examine the intraocular pressure and to tell whether you are in the development of the glaucoma. And if earlier detection can be treated because it can be easily fixed because it's basically it's a flow issue, and maybe something stuck the flow, so it can be easily fixed if we detect it early. And in addition to this humor, the aqueous humor, we also have another humor. It's called vitreous humor. This vitreous humor is less clinical relevance. The reason we need to mention about it is because it's big. About 3/4 of this eyeball is the vitreous space. But you need to know that this space is not like flow, it's not like living water. It basically is isolated. So that's that. And so we mentioned about it to know that this is not the one to conduct the intraocular pressure. The intraocular pressure is not because of this vitreous space. It's because of the anterior chamber and the posterior chamber where we have this aqueous humor. So that's that. And then we moving away from the cornea toward the back of the eye, we talk about the sclera. Sclera is a connection, is an extension from this cornea. So from the transparent window to the wall, that wall is the sclera. And that is the white part we see in the eye. And what we need to know about this sclera is that, why do we need to know about it? It's because it's an extension from the dura mater. And basically that's everything linked with the brain. And that is essential because that makes the retina as part of the central nervous system. Everything within the dura mater is the central nervous system. And that's important. A related question would be that concept is that if there's any neuronal damage in the retina, it's considered as the central nervous system neurodegeneration. And why is that important? Because in the peripheral nerve degeneration can regenerate. The peripheral axon is very good at regeneration, but in the central nervous system, regeneration is almost impossible. That makes the glaucoma, this disease, is a central nervous system neurodegeneration. Once it starts to degenerate, there is no turning back. So early detection is very important. And also another thing is that the major difference between central and the peripheral is in the myelin. So in the central nervous system, the myelination is oligodendrocyte. The peripheral is Schwann cell. We don't really have myelination in the eye, but the optic nerve is the one, moving from the eye toward the brain. There is still some distance, not reaching the brain yet. However, that distance still wrapped by the oligodendrocyte. So all the myelin related to the eye are all oligodendrocytes. So that's that. So make the retina part of central nervous system, CNS, the central nervous system. And then we talk about the lens. The thing you need to know about the lens is the accommodation. And this one is, one thing you need to know is that it decaying in age. Then we talk about the refractive disorders. We talk about this because of this accommodation is not perfect. It will lead to the refractory disorders. It include the myopia. Probably everybody, 99%, 99%, a lot of people has the myopia, that the vision cannot project onto the retina, but a little bit too early, too anterior, too front. And hyperopia is the one opposite, project to the back, and this can be easily corrected by wearing a lens. Then we have looking into the retina. This is the neuron portion of the eye. And then we talk about different location in the retina, including the macula. Macula is the center of the eye. Basically, when we have the visual seeing a point, a fixing point, the center part project into the macula. What's the unique about the macula is that that provide the highest acuity of the vision. And the fovea is the center of the center. So macula is the center. If we look into the fundus image, we see it's a little bit dark, and that's the name coming from. And then in the center of that is the fovea. We also mentioned about the blind spot. So this could be an easy quiz question. Where is the blind spot? We have the blind spot in the retina. The blind spot is the optic nerve head, because that's the region optic nerve will enter through the retina into the brain. And so that region doesn't have the photoreceptor. So that's the blind spot. Then we talk about the retina layers. Here we show 5 types of cells, from the photoreceptor to bipolar to retina ganglia cells. So that's the signal pathway. Photoreceptor detect the light, release glutamates, excite the bipolar excite the retina ganglia cell. Retina ganglia cells send axon to the brain. So that's basically that 3 major cells. We also have 2 interneuron, 2 inhibitory interneuron. So that total will make it 5. And then there are 7 layers. What do you need to know about this? Well, so you need to know a sequence. You need to know that, signal conduction sequence. Photoreceptor to bipolar to retina ganglia cell. Because that's an easy question, right? Easy. I can easily design a question to ask that, because I can randomly put them around and to see which one is correct. What else? Yeah, that's probably the one. Okay. Layer is it's 7 layer. I probably won't have a question on that, but you need to have concept that their retina is a way to organize in a way that it has layers. Okay. Then we talk about these photoreceptor. Then we start to talk about this photoreceptor is the one to detect the light. And what do you need to know about a photoreceptor is that it includes two types, the rods and the cones. So here we can have many questions. So rods detect light, sensitive to light. We have three types of cones. They are sensitive to the color. So that's that. And then here we talk about how are they depolarized. They, in fact, depolarization in the dark. So light actually make it hyperpolarized. So that's something you need to know, that it's kind of opposite to our general understanding in the nerve, that it has to be excited in order to generate depolarization. But in the photoreceptor, it's opposite. It continuously excited until you open your eye. Okay. So that's that. And also with this depolarization process, we mentioned about the retinoid, and that is the one to we talk about the rhabdin and the photopsin, and by there we talk about this unique molecule, 11-cis retinol, and that once it's used, it will become all trans retinol, and we need to replenish it in order to supply that molecule to our eye. And one thing you need to know, this will be relevant to your own health, is that taking sufficient, because we can replenish those by the diet. Vitamin A is a good source to provide that. So that's that. And then photoreceptor, the next up is the bipolar. That's this one here. And the next up is the, sorry, that's the end, bipolar. And before we talk about the bipolar, we mentioned about this retinal pigment epithelium. This is the one underneath. Maybe it's easier just showing you the slide. Let me see if I have the slides here. Okay. Sorry. All right, so let me put this one here, and let me, you don't have this slides on the screen, right? I need to, no, okay, good. Let me share screen here. Oh, I did not share screen at all, man. I did not. All right. I thought I did. All right. Okay, so this is the, I was talking about the outline, but here is the eye. Then basically that we talk about this layer, right? This layer, and the 7 layer, 5 type of cells. We then talk about the photoreceptor, the rods and the cones, and then we talk about how they are different. So this is a good summary table right here. Rods is more sensitive to the light, cone is sensitive to the color, and they are 3 type of the wavelengths, the RGB, red, green, and the blue. So we have 3 type of the sensor. The sensor is called the opsin. So it could be the rhodopsin. That's for the rod. Here, rhodopsin. Where is that? Rhodopsin. We also have the photopsin. This is one for the color. And in this opsin, it contains this molecule. That's one I want to show you. It's molecule. This molecule is called the retinol. So it was the 11-cis retinol inside of this opsin. And once light shines on it, it will convert it to the all-trans retinol. And this all-trans retinol will not respond to light anymore. So with this one is just one-time use. You use it, and then you cannot use it anymore. So we need to find a way to replenish this molecule. And our body basically has two ways to do it. Our body can do one way, maybe two way, one way, maybe one way. One way is the one that we talk about, RPE, retina pigment layer, that is underneath right here. Let me show you, maybe layer, where's layer? Okay, layer here. Underneath the photoreceptor. So here is light, here's vitreous, light going in, hit the photoreceptor, and that will trigger the photoreceptor to transduce signal. If there is extra light, here is the pigment epithelium cell. Why is that pigment? Because this color protect our body. Once we only need light to stop here, we don't want it to penetrate. Otherwise, it will damage our body. So this color absorb the light, it protect us. And this retina pigment epithelium can also replenish part of this used retinol. And so that is this one. That is this one. Let me show you this one here. So this is one showing you that this is the outer segment of the photoreceptor. It used this 11-cis retinol to become all-trans retinol, and this all-trans retinol will be carry over through the RPE, retinal pigment layer, and then convert it back to the 11-cis, and then our cell can use it again. So that's one way that our cell can replenish it. Otherwise, it's used, it's gone, we cannot reuse it. Another way it's very important is the diet, because vitamin A contains this 11-cis retinol. Our body can digest it and convert it to the 11-cis retinol. And so that is these right here. So the beta carotene is one can be digested and be used by our body to produce these 11-cis retinol. So that is that. Let me do it. Any questions? Hey, Joseph, you're back. I saw it. Yeah, he's the one that had an accident early in the quarter, in the class. All right. So what else? Let me see. Let me share another. Let me do this one here. Share screen. Share screen. Screen share. Screen 2. Use this one. It's probably easier. All right. So I share the entire screen. So that's the one that we talk about. So I can make this one smaller, so everything will fit into this window. So that was the one, here is one. Now I can probably make this one smaller too. All right, so that's that. All right, so you have both, right? The PowerPoint slides and also the outline, right? Okay, so that's the one I went through: cornea, aqueous humor, lens, accommodation, retina layer, photoreceptor, then RPE. All right, then RPE has can conduct two important things. One is, of course, it has pigment, so it absorbs light. The other two new is that they can replenish the 11-cis retinol. This is called the retinoid cycle. It can also do another thing, is to eat their neighbor. Wow, that is weird, right? Eat their neighbor. That's right. That you hear it right. They eat their neighbor. So that's right here, and they eat it regularly, like 3 meals a day, 7 days a week. So it's like this one here. So you can see that this is the photoreceptor. They have this outer segment. We call this portion outer segment. A photoreceptor had 3 segments. We have this, let me show you here, outer segment. This outer segment contains a lot of these discs. And these discs basically generate more membrane in order to anchor on the rhodopsin and photopsin. And here is the inner segment. Inner segment contains mitochondria and the nucleus, right? So this outer segment is embedded in the RPE. And right here, outer segment is embedded in the retina pigment RPE layer. And now this RPE help them to replenish the 11-cis retinol. They also eat it. All right, so that is right here. This is called disc shedding. Disc shedding like that. So this is the outer segment. This is kind of like upside down. If you flip it, you can see this outer segment embedded in the RPE layer. And then they will chuck about 1/10 every day. You know, it's regular. Take it out, eat it, digest it. Yummy, yummy. That's that every day. Okay, so that's how you love your neighbor. You eat them every day. And then so that's the very unique part of the RPE. And why is that important? Because in addition to replenish these 11-cis retinol, there will be accumulation of some toxics. And you need to know one thing about this retina is that this entire retina has no blood. So you have the blood supply on the top and on the bottom, but not in the middle. Let me show you this figure here. So entire this retina doesn't have the blood supply. Blood doesn't go through it. So maybe I have a picture here. So you can see that the blood will go over the retina and go under the retina, but not go into the retina. So, and the photoreceptor is one to conduct a lot of this energy consuming process. You need to convert the photon into electron. So that generate a lot of the metabolic waste products. And so the way our body to remove those waste products is to have this macrophage going on by this RPE. So that's that. And then, so that's called a disc shedding. All right, go back here, disc shedding. So that's that. All right. So maybe a quick question is that disc shedding is who eat who, right? It's the RPE digest. Eating is a easy way to understand, but is to digest part of this photoreceptor outer segment. So that's disc shedding. So that's the RPE, and then what you need to know, then the next is the bipolar, and this property is important, and that's the also very interesting topic that we need to know about the eye is the bipolar cells. Bipolar cells has 2 types. One is called on bipolar, the other one is called off bipolar. So it means that we have 2 And the way to memorize it, if you don't go through all the detailed molecular process, the way to memorize it is that on bipolar is when there is light. This bipolar turn on. It generate. Their next stop is the retinal ganglia cells. So when there's light, bipolar will release neurotransmitter to excite the retinal ganglia cell. As for off bipolar is that when there is no light, this bipolar will generate action potential and to release neurotransmitter to act on the retinal ganglia cells. So that's the easy way. On and off is by their action. When there's light, they're on. When there's no light, they're off. If we look into the molecular process, it will be a little bit more detail to it because we know that the photoreceptor acts opposite already. Photoreceptor is one that when it's dark, it releases glutamate. When there is light, they don't. So that's the we mentioned about this process here. But if we in terms of the exam, what you need to know is that this bipolar has two types. Okay, when there is light, the on bipolar turn on. When there is no light, off bipolar turn on. Why do we need to have two types of the bipolar? Why do our eyes sensitive to both light and dark? This tells us the idea that our retina, when we close our eye, part of this bipolar trigger the retinal ganglia cells. When we open our eye, the other part trigger the retinal ganglia cell. So there is always some signal sent to the brain, even if you close your eye. So when you close your eye, you feel that you are seeing something, you feel it, right? Your brain get the stimulation by the dark. Those dark off bipolar will send signal to the brain. Why do our eye want that? Why is our eye designed that way? It's because that when we see anything, there is always a contrast. It's not planned. We see things, part of it is dark, part of it is bright, part of it has different color. And the way we see things is that you need to consider that our photoreceptor can also have this adaptation, meaning that when we see things for a long time, that stimulation go away. It's very much like our somatic sensory. When you touch things for a long time, that stimulation will decay. It may not be completely gone, it will be decayed. So the way we see things is that we see the contrast. So later we will talk about next lecture, we will talk about a concept that our eyeball actually continuously moving all the time, even though we think that the eyeball is stationary. It's moving all the time. So we basically, when we see things, our visual field keep changing. And so we have stimulation from the light, but that decayed, we then move it to the dark. And so by doing so, we are very good at detecting the contrast. We are very good to appreciate the contrast of the imaging. If the contrast, if the edge is blurring, we start to feel that things is blurring. We are not very good at identifying the center of the color. We focus on the contrast. So that's how we see things. We see the edge. If the edge is clear, we think the picture is clear. If the edge is not clear, we think the picture is not clear. So that's the concept. And in the end, what you need to know is this one here. So the retina circuit basically contains three major signal pathway. In the somatic sensory system, we mentioned about the first order, second order, third order. So we don't really talk about the first, second, third order here in the visual system, but the similar concept would be the first one is the photoreceptor, the second one is the bipolar, and the third one is going to be the retinal ganglia cell. And then retinal ganglia cell will send axon to the to the brain. So it's right here. Let me show you it right here. So that's right here. So this is the retina. This is the retina ganglia cells. They send axon forming a bundle. This one is the optic nerve. This optic nerve start to have myelination. This myelination is the oligodendrocytes. They penetrate through the retina, enter into the brain. And so that is the blind spot because here we don't have the photoreceptor. When the light project into the optic here, light penetrates, project onto the optic nerve head, that's a spot we don't see. If we using only one eye, we probably could be able to identify that spot. But because we have binocular that we have two eyes, so the blind spot will be seen by the other eye. So we don't really feel that there is any blind spot in our visual field. So that's that. And the next one is, let me go back to this one here. Any question on this? The eye part. All right.
I have a question.
Yes.
Hi. So I got a little confused on the bipolar cells.
Yes.
When it said glutamate receptors cause, for on bipolar, it said glutamate receptors cause, sorry, hyperpolarization, but then it's bipolar depolarization. And then for off bipolar, it's glutamate receptors cause depolarization, but then bipolar hyperpolarization. I got
yes. Okay, that is good question. All right, so you need to think about. Let me use the picture here. So I assume this is the one that you were talking about. This is the one, right? Something like this one. Is that right? Okay. So you need to think that. Let me explain this one. Okay. So you need to know that this is the bipolar. This is the RGC. And on the top of it, we have the photoreceptor, right? Photoreceptor, right? This is a photoreceptor. Now, when this is unbipolar, let's just say this is unbipolar. So meaning that when there is light, there will be no neurotransmitter. When there is, so this is off. So this is no light, dark. When there is dark, this one release neurotransmitter. Right? So when there's dark, the photoreceptor release neurotransmitter, and then this neurotransmitter will act on both of bipolar, acts on this bipolar, and its dark neurotransmitter will act on this bipolar contains the AMPA receptor. This one is the glutamate receptor that we learned before. It acts on it, then it will cause depolarization. Sodium will go in, it will cause depolarization, then it will cause it to release neurotransmitter, the glutamate again. This glutamate will act on the RGC, so this is the RGC. And then the RGC will get excited. Sorry, let me see it. This is off bipolar, and what did I say? AMPA receptor, the calcium coming in. Yeah. So yeah. So this one is that this says it's light. So if there's light, when there is light, I know this is a little bit confusing. So this it will release the neurotransmitter, right? And if there's dark. If it's dark, then it will opens up, and then it will get excited. But if there is light, then light will make this photoreceptor don't release the glutamate. If they don't release the glutamate, then they will not. They will the bipolar will not get excited. Then bipolar is not getting excited. There will be no neurotransmitter get released, and then the RGC will be hyperpolarized. So that's right here. So if there is dark, it got hyperpolarized. But if there's light, if there's light, the RGC get depolarized. If there's light, it got hyperpolarized. So this one includes two conditions. If it's dark, this is the dark. Here it's dark. So if it's dark, then the photoreceptor will release the glutamate, binds the AMPA, then the bipolar will release the neurotransmitter, causing the RGC to get depolarized right here. Does it make sense? Okay. And if there's light, then this one will not release the glutamate. Glutamate will remain here, not getting released. Then there will be no glutamate to bind the RGC. Then the RGC will be hyperpolarized. So that's the off bipolar. That when there is light, the RGC is inhibited, it's hyperpolarized. Does it make sense? Any questions? Okay, good. All right, so that's the off bipolar. Now the on bipolar is different. Let's see the on bipolar. The on bipolar also has a condition that there's light or there's dark. Say if there is on bipolar, say if there is light, then light will make light will make this photoreceptor not sending out the glutamate. With the off bipolar, the receptor is an inhibitory receptor. So this is the glutamate. When there is glutamate, it actually can cause the hyperpolarization. So when there is no glutamate, when there is light, no glutamate, this channel would remain open. And when they remain open, the sodium will go in. And then when sodium will go in, it will cause these cells to release the neurotransmitter. Neurotransmitter will bind on it, will cause the RGC to get excited. Okay, and if it's dark, then the photoreceptor will release the neurotransmitter. Neurotransmitter will bind on the receptor, and because this receptor is an inhibitory receptor, it will close up this channel. And then if it's closed up this channel, there will be no excitation in the bipolar, and there will be no neurotransmitter released. And then the retina ganglion cell will be inhibited. It's not getting excited. So if it's dark, then it will be not excited. Consider that it's not excited. And if there's light, then it's excited right here, depolarized. So that make it on bipolar. Any, is that clear? Okay, good. Yeah, all right. So that's
Thank you.
all right. Good. I know it's difficult to go through because the key here is that this glutamate has the bipolar has two type of the glutamate receptor. One is the AMPA that we commonly see, and this is a different type. This is an inhibitory glutamate receptor, and yeah. So all right. All right. And any other questions? Okay. Now the next one is the so with this one we will start to explain several visual pathway. Let me drink some water here. Several visual pathway, and that includes, so basically that visual pathway, we talk about this retina portion, kind of overview about it. And then we learn about this is the visual pathway into the brain, include, and we first look into where do they innervate. They innervate into different portion, indicate that they have different function. So what's their function? So the first is that look into here, the neural circuits related to the eye. So we talk about the visual pathway, that's the major one, the primary signal transduction from the RGC, so it's the brain RGC, retinal ganglia cells, to the LGN, lateral geniculate nucleus, then going to the V1, the visual cortex. And then the other is that we have two reflexes not related to the eye movement. One is the pupillary line reflexes. So we talk about that circuit. The other one is the regulation of the circadian rhythm. And so that also related to another circuit. If you don't mind, I will mute you. All right. Okay. Okay. Thank you. All right. So the other reflex is about other reflex related to the eye movement. So including the physiological nystagmus, this is the one that I mentioned earlier, that our eye continues moving in order to find the contrast. The other one is the saccaded movement. That's the one that our eye can quickly move from one spot to the other spot. Smooth pursuit movement is the eye can trace a moving object. Vergence movement is one that our two eye can be controlled to focus on the same thing. Vestibular movement, or it's called the vestibular ocular reflex. We will also talk about this one in the vestibular system. It's not, this will be next week. And this one is that a movement of the eye actually driven by the vestibular apparatus is this one. So we see things, we turn head, we can focus our vision on the same visual field. And that's this one. And because that the vestibular system detect the head movement, and it will move the eye to the same magnitude but opposite direction. So if our head moving to this way, it will tell our eye to move the same magnitude but opposite direction. And by doing so, we will fix our vision all the time. And this is not driven by the visual. It's not we're trying to focus on something. It's driven by the vestibular. All right. So that's that. And so the first we talk about these popular life reflexes. When we talk about any reflexes, something that we need to know is that the input pathway, the center, and the output pathway. The earlier reflex that we mentioned about is the stretch reflexes. The input is the somatic sensory, the output is the alpha motor neuron, the result is the causal contraction. And so same thing here. If we talk about the reflex, there's input, there's output, there's a center. In the stretch reflexes, it's very simple. It's the simplest one. That's called the monosynaptic reflex. And that really doesn't have a center. It directly triggers the motor to respond to it. With this one, the input is the optic nerve, the cranial nerve 2. The center is the pretectal nucleus, and then output is the oculomotor pathway, cranial nerve 3. And what you need to know about this is that very important is that it's binocular, it's bilateral. So it's first is that the stimulation is not on common RGC, it's on this melanopsin containing RGC. That is the RGC sensitive to the light. The other RGC respond to the photoreceptor, but this RGC is sensitive to the light. This is called the melanopsin containing. We only have about 1% of this type of the RGC. And what else you need to know is that this is bilateral, meaning that if the light shines on one eye, it will cause both pupil constrict. So the doctor, physician doesn't have to check on both eye. You can check on one eye to see if both eye have this pupil constriction. After this one, we start to mention about this sympathetic, the autonomic control, because the pupil constriction is the muscle control, but not controlled by our intention. So it's not a voluntary movement. This is the autonomic movement. And this autonomic movement must be controlled by the autonomic nervous system. And then autonomic has two branches, sympathetic and parasympathetic. In terms of the pupillary light reflexes, the sympathetic will make the pupil dilated, because when we are in the sympathetic, meaning that we are in the fight or flight mode, that we need enough light to stimulate us for prepare us to see things clear. So that's pupil dilation. If it's parasympathetic, we will cause pupil constriction. We don't need that a lot of stimulation. And so here we explain this sympathetic versus parasympathetic. We already know that sympathetic will release norepinephrine as their major neurotransmitter. Parasympathetic will release acetylcholine as their major neurotransmitter. But how do they control pupil dilation and the constriction? So we explained it here. So it's on page 13. So if you look into the 13, you will see it, 13, right here. So that's this one. And what you need to know is that sympathetic and the parasympathetic acts on different group of the smooth muscle. Sympathetic acts on the radial dilator or radial muscle. The parasympathetic acts on the circular muscle. So when the circular muscle, the parasympathetic will excite the circular muscle to cause smooth muscle constriction that will cause constriction. And the sympathetic will act on the dilator muscle. When they contract, they pull this pupil large, and that will cause pupil dilation. So that's that. And then we talk about the circadian rhythm. Circadian rhythm is related to the biological clock that our body have, but we also are able to adjust that biological clock when we move to different time zone. What's the mechanism on that? That is the light. light affects us to adjust these circadian rhythmicity. So, and what you need to know is that the nucleus to affect this biological clock is this suprachiasmatic nucleus. This basically is located right near the chiasm. That's the chiasmatic that term coming from. And that receive the signal again from the same type of the RGC, the melanopsin containing RGC. And so even though the person is blinded, it doesn't have the photoreceptor, cannot see, they still are able to detect the time zone, detect the light, to conduct the pupillary light reflexes, and also control to regulate their circadian rhythm. So that's that. And then we go back to talk about this primary visual system. We then talk about the visual field. That's a field we see. In the somatic sensory system, we have the concept about the receptive field. That is how near you can distinguish two different stimulus, and that indicate how much overlap of this receptive field. Visual field is characteristic effect of that. You see the whole thing. Each retina will have its own, each RGC has its own receptive field, but overall you have the visual field. And then we talk about this visual field. What you need to know about this is that our visual field is very exact, like the way we take the picture. What we see project into the retina. If there's a film in our retina, it will impose those light and to get the picture on that film. The way we do it is a digitalized way that we excite the photoreceptor and generate that picture. And then what you need to know is that that picture is upside down of what we see, left to right of what we see of the visual field. Maybe I have a picture here. So that is this one here, this one here. So this is a visual field. Retinoptic map in the retina is upside down, left side, right. And we have binocular. So this visual field contains left visual field, right visual field. The center portion is binocular. That is the overlap of both left and the right eyes. And this visual field project into the retina, then project into the lateral geniculate body or lateral genetic nucleus, then project into the V1. This is the visual cortex. And then what we also need to know is that RGC has 3 types: the M type, P type, and the K type. N type is sensitive to the M type is in the central, is sensitive to the color. So let me see here. Maybe make sure that what I say was. Sorry, M type here, right here. M type is in the peripheral. M type is in the peripheral, sensitive to the motion, and not so sensitive to the color, because in the retina, our center is containing a lot of cones, but in the peripheral, it's more like rods. So the M type is sensitive to the peripheral, is sensitive to the motion. The P type is more sensitive to the color. They are located in the center. And they project into the retina LGN, lateral genetic nucleus, in different layer. The M type project into the magnocellular. So M type has high adaptation, fast adaptation. P type has slow adaptation. they project into the M-type project into the right here, magnocellular layer, and the P-type project into the parvocellular layer in the LGN. So this is the LGN, has 6 layers. The M-type project into the magnocellular layer right here, the P-type project into this parvocellular layer, and then they all will project into the V1, the primary visual cortex. The V1, then we talk about the V1. What we need to know about the V1. So the V1 has 6 layers. It's like a somatic sensory cortex. The input signal is in the layer 4. What you need to know about the V1 is that they are sensitive not to the object, not to the point of the vision. They are sensitive to the orientation of the visual field. So the idea is this one here. So how will we know it? Because we put, in the beginning, we use cat as an example, as a way to experiment it. We put the visual field, we put a bar. This bar has a certain orientation. However, a visual cortical location only sensitive to a specific orientation of this bar. If we put the bar this orientation, we get a strong signal from that column. If we move this orientation to a different orientation, we lose the excitation. So each column of the cortex is sensitive to the orientation of your visual field. So say your visual field has different thing, right? Has horizontal, vertical, different thing. What you will expect is that this different bar excite different column in the V1, in the visual cortex. And this gives us an idea that what we do see is not point by point. What we actually seeing is the contrast of this line. When we see things, we see profile. We see the eye profile. We see the figure profile. We don't see dots. That's the amazing part of the visual, and that is something that may be able to be used in your clinical, because when you want to get an attention of your patient, you can try different orientation of this object and some motion to it, because the motion is quickly picked by the peripheral peripheral retinal ganglia cells and the peripheral retinal ganglia cells, and also different orientation can excite different portion of the visual cortex. And so that lead to these concepts right here. So this is the visual cortex, has different column. Each column is sensitive to different orientation of this bar. And so that specific orientation of the bar to that column is called ocular dominant column, dominance column. So it's orientation column. Each column is sensitive to different orientation of that bar. So that's the thing you need to know about the V1. And then after V1, we also has an associate visual cortex. This is called the extrastriate cortex, because V1 is also called striate cortex. And then what do you need to know about this extrastriate cortex is that there are 2 streams. So right here, 2 stream right here. So when we see things, we get an orientation in the cortex. we get the picture projection to the retina, to the LGN, but when they project into the retina, they enter into the layer 4, but layer 4 start to process to layer 1 to 6. And in the layer 1 to 6, they start to arrange what they see. They start to process it. And by V1, what you see is already not the picture you see. It's already oriented, the orientation driven stimulation. And so that's what you see in the V1. Now, our brain will try to interpret what you see. It's a process. When you see things, it's not one way direction. It's not totally passive receive the signal. It's a process of our brain to understand it. We see things, we see three-dimensional process, we see object. We identify this object away from the background so we can see this as an object. And that leads to this extrastriate cortex. And so this extrastriated cortex has two streams. One is the V1 to MT middle temporal area. This one is sensitive to the speed, time related, temporal related. So this one will see things, but not just 2D, not just 3D, but 4D, four-dimensional. It will see things, compare the first move to the second move, to the third move, and to calculate the time and the position relationship, and to understand this moving object. When you see things, it's like a movie. Each one is a stationary frame, but when we collect them together, it's a moving object. One is a moving object, the other one is the background. So we can identify that moving one from the background, and that is conducted by this dorsal stream, V1 to MT. We also have the ventral stream, it's V1 to V4. This one is not speed related, it's not time related. This one is to recognize this object. And so coming to the temporal region is a region also related to our memory and a lot of emotion, cognitive process to it. And so that is a place that when we see things, we start to interpret it based on our understanding, our memory, our history, our experience. So that is that. So this is another, and that's why that the amazing part about the vision, I really like and I really feel how true this verse is, like in the Bible, that we pray to Jesus. A lot of like blind people pray to Jesus to get healed because of the vision. I don't remember any other disease. There are cripples, they cannot move, but cripples that they cannot move got healed. But a lot of time, this healing is about blindness. I remember several cases, right? How Jesus healed the person who is blindness. I think it's not just that single event. Vision is something that we really need helps, because even a lot of time that we see things, but we actually don't see it. We don't see it clear because of our bias, be honest, because a lot of this interpretation is because of our experience about our memory. And this also leads to, that's why I feel like a lot of time we need to, it will be a good thing that we can really open our eye to see a lot of things that, God presented to us, or to see, more important is about your direction, your future, what you're gonna do, what's the right thing to do in the next. So that's that. And that vision is very important. It's very like pleasant to have. Another thing about this is about the art. That's something also related to this. Say you have the artist, right? You want him or her to draw things, to paint things. Why do we have someone drawing very real, but someone like Picasso? He saw a beautiful woman, but the painting presented is something totally different, right? You would think that, but why is that painting so valuable? It's because that painting resonate with you. You feel it. Why do you two people or some people resonate on something that doesn't look like reality, doesn't look like what you see because of this interpretation? When we drawing, we can base on the V1. It's already not. We can base on the LGN, lateral genetic nucleus. That is a real picture. It's a very royal presentation of the visual field. But down to the V1, we already enhanced the orientation. Down to the V2, MT, V4, it's already adding a lot of interpretation to it. However, that interpretation resonates with people. Yeah, so that's the beauty of the art, that people can draw a thing based on their deeper portion of that visual cortex, and by doing so, they actually can resonate with the viewer. So visual is very interesting. To me, it's one of the most interesting in the sensory system. Another interesting portion of sensory system is the audio. We don't have time to talk about the audio because I'm very interested about how music resonate with people. Why this song become a hit, but the other song fail. That's also something related to our resonation. How do we resonate with a song? And so that's that. But we are not going to talk about the auditory. So that's the vision. What else? And that's it. In the end, I talk about this visual agnosia to give you some entertainment. Here I provide you 2 videos that you can take a look. You will be amazed because we didn't really see a lot of this disease, but there are people. There are 2 extremes of the people. One extreme is that they memorize facial very good. The other extreme is that they cannot memorize the facial. And another extreme is that they cannot distinguish the facial from the background. They cannot distinguish the object from the background. So it's like you have the picture, its line and the dots, but how would you connect them to identify that object? So that's something also related to the ventral stream, dorsal stream, that to identify this object. So that's that. Any questions? All right, then that's it. So we will have a quiz about this visual portion on Friday, and I will post the final one. The final one will contain 3 lectures. Okay, and that's it. Okay, that's it. So it's not like extra work. It's those 3, and then we have. Let me see the calendar. I want to close this screen sharing because I don't want to show something that I don't want to show. Hey, there's chatting. Let me see. What's the chat? Have you ever heard Holmes-Edis syndrome? Okay, pupil to be frozen so it never constrict or dilated. Okay, I can go check. Yeah, that's not sure what's the causes, but
Well,
hey, you want to share something? Yes, go ahead.
So my husband's actually sitting right next to me. He has Holmes-Addy syndrome, which the pupil will randomly freeze, and it doesn't happen to both eyes. So one eye will be frozen, and then the other eye will work, dilate and constrict. So it looks like he's had a stroke or something.
Yeah.
But then recently his other eye froze. So it's like his pupils are like different sizes, but they don't ever constrict or dilate. They don't know the reason actually. They just know that it has to do something with the nervous system, but they haven't ever come up with a reason why. And there's no treatment for it either. You just have to deal with it. So
How is that he or she?
my husband.
Yeah, oh,
Yeah.
How is his daily life? How does he overcome that kind of
The sensitivity to light, he uses sunglasses.
Oh, okay.
He can't go outside without using sunglasses. He also can't be in a very bright room either.
Oh, okay.
It doesn't affect his visual.
Yeah,
He can
acuity
still,
is not
like-
affected.
Yeah,
Acuity is not.
nothing else is effective except for the fact that he can't go outside without being
Okay.
blinded.
Okay. Yeah.
I just thought I would share something fun since we were going over the eyes.
Sure. Yeah, I appreciate that. Yeah, thank you. Yeah. All right, then. Let me unshare this one very quickly, so I can let me do that. Stop sharing, and let me check my calendar. So basically, that we will have just make sure that we guys we have a good idea that how are we going to finish this course. So this Friday we will have quizzes on the visual system, and then beginning say tomorrow I will post 3 lecture about the motor. 3 lecture will be basically will cover this the one that we planned in the lower motor system. So the very first lecture is lower motor system. The second lecture I already posted. If you go to the YouTube, you probably saw it already. The first is the lower motor spinal cord. The second one is the vestibular cerebellum. The third one will be the basal ganglia and the cortex. So that's that. So we will have a quiz on Friday, and then we will have the lecture on the next week and the quiz on 20th. And then we will have the final exam on the 23rd. So that I think that's a good way to analyze and finish it, because you will have quiz on every lecture. You will have a quiz on the visual this Friday. You will have a quiz on the motor next Friday. So you know that what is going to be in the final. You know the range, you know the style, you know it won't be the same, but you know relatively you have a confidence that the final is here. If you handle all these quiz questions, you will be okay. You know, you will be 80% at least. And if you handle this online well, you will be 90% okay. Yeah. So that's that. So that then we will finish it. And so you have the idea that what's gonna be happening, and because it's not just my course, you have other courses, so you can start to plan your time and to allocate the time. To me, as long as you work on the lecture week by week, you will be okay. You don't need to have accumulate stuff to study it just at one night or something like that. All right. Any questions? So I will see you again next Tuesday, right? All right, good. Yeah. All right. Then if there's nothing, then that's it. Bye-bye.
Thank you.
Thank you. Bye-bye.
Thank you.
All right. Thank you. Yeah. I really
Bye.
appreciate you guys coming, showing
Oh,
up.
I appreciate you.
Yeah. All right. Bye.